Hello everybody. In today's lecture we will continue our camera geometry discussion. We will finish it up and then we will start talking about the processing the images that we have produced with this camera. Last time we talked about the homogeneous coordinate system and its usage. We said that with the help of the homogeneous coordinate systems, we can now represent points on at the infinity. Okay, and we can talk about the points at infinity like the regular points, and in our equations such as the homography equations, we could use them with no problem. And this was one of the examples of how we use the homography. And I think last time I told you that 4 points are enough to find the homography, between these two images. That's what I said. But the points that we have chosen are the regular points, but we could have done this. Let's say I have two parallel lines. Let me use the green color. This is a line, parallel line, right? And this is another line. And I know that these will, if I continue them, these will intersect, right? In reality, they should not intersect because they are parallel in real world, right? They should not intersect. But in this one, I think it's going to, if I continue, let me exaggerate a little bit, it's going to intersect here. Okay? So the corresponding point, I just did the opposite. Okay? The corresponding point of this dot here is going to be the intersection of these. Let me use blue color for that one. Okay, intersection of these two blue lines. Well, these two blue lines will not intersect because these are parallel. That's what I'm trying to do. But using the homogeneous geometry, homogeneous coordinate system, I can find the intersection point at infinity, and I could say that the intersection point of these two blue lines and the intersection point of these two green lines correspond to each other. So as one of my correspondences, I could use that one. So it is going to be something 0, right? A comma B comma 0 is the intersection point of this one, and I can use that in my equations here. Okay, so points at infinity could be used for establishing homography, and your homework actually includes that one. I didn't assign your homework yet. I have written it after the class. I will post it. Okay, so more examples of homography. Your homework is about this one. Okay, so if you have images, two images of the same planar surface, there is a homography between this plane and this plane. Also, there is a homography between this plane and that plane. Okay, so this is the image plane, this is the image plane. I have two image planes because I have taken two pictures, and there is one image plane, there is one planar surface in the real world. So the one homography H1, okay, will transform me from this space to this space. H2 will transform me from this space to this space. Okay, to get the homography between these two, what do I do? On image 1, okay, I have a point. Image 1, I have a point. To transform this point from image 1 to the planar surface coordinates, I would multiply that point, let's say this point x here, right? So x times h1 would give me the capital X. Okay? And then if I use h2 times capital X would give me x prime, which is this one, right? But if I like to find a homography between image 1 to image 2, what would I do? Is anybody talking? Because is my speakers off?
We have to find a transformation matrix of homography.
Between image 1 and image 2. That's what I am asking. How do you find it? If you can run just find homography of OpenCV, that's fine, but there is a much better way of finding it. I like to find H3 between these two. How do I find it?
We can just multiply H1 and H2. Right?
Exactly. What is X? It is X times H1, right? I mean this one. So what is X prime then? H2 times H1 dot times X. What is the size of H1 and H2? What is the size of H1? As a matrix, what is the size of H1?
3 by 3.
3 by 3, and this one is 3 by 3 too. If you multiply two 3 by 3 matrices, you're going to get another 3 by 3 matrix. So if I say H3 is, okay, H3 is H2 times H1, then to get X prime is H3 times capital X. Okay? So that's the beauty of using homogeneous coordinates. It makes these kind of stuff a lot easier. Okay? So remember, this is a planar surface. Okay? This is not, I mean, all the points are on the same surface, planar surface. They are not freely moving, right? If they move on the same surface. This kind of homography is not valid for arbitrary points, like there is a point there, there is a point there, there is a point there. I cannot find the homography using these kind of points between these two images. This homography is only valid if there is a planar surface like that. Okay. For example, there is a homography between this image and that image. That's fine, because these are two planes. If I know the correspondences between the points of these images, I'm going to find it no problem. And the same thing is here. Okay, I know that they each correspond to each other. Okay, also there is a homography between this shadow, because it's on a plane, and this side of the building. Okay, there is a homography between those two. But homography for the homography to exist, you need a plane. Okay, without the plane, there is no homography. And we are going to say this in our stereo chapter. Okay, so last time we looked at this, we said that using the homogeneous coordinate systems, we can handle the perspective projection. If I multiply this real world three-dimensional point, of course this is in three-dimensional point, but it is expressed in 4 dimensions because this is in homogeneous coordinates. If I multiply this with this matrix, very simple matrix, I would get this three-dimensional point in three-dimensional vector in two-dimensional world, homogeneous world. Okay, so this is in 3D, three-dimensional world. This is in two-dimensional world. This is in homogeneous coordinates. To convert the homogeneous coordinates to the non-homogeneous coordinates, what do? I divide x by minus c over d. This is what I get, and this is what I get. And if you remember, this is what we have. This is what we our derivations produced this before using the similarity of the triangles. And there is no single way of achieving this. In fact, I can use a 4x4 matrix with this one. Okay. What I input is a three-dimensional homogeneous coordinate. What I output is a three-dimensional homogeneous coordinate. But if I like to get the non-homogeneous coordinate, what would I get? I would get x and y. This z is going to be ignored because z is lost with the projection transformation. Even if I do that, if I divide z by this one, all I would get is just d. Okay, that's d. Whatever you do, it is independent of z. Okay, so homogeneous coordinates are very useful with projection matrices. Okay, so perspective projection is handled this way. Don't forget this one, and we will use different versions of this all over. Okay, so this is perspective projection. There is another projection type. It's called orthographic projection. Orthographic projection, it just loses the one of the components, just z. Just lose it. This is what we do. 1 1, okay, 1 0 0 0, 0 1 0 0, 0 0 0 1. Multiply the three-dimensional homogeneous coordinate, and I would get this one. And if I divide x and y by 1, I would get this. So z is lost. Okay, this is called parallel projection. What is the difference between perspective projection and parallel projection? This is, where is my perspective projection image? Okay. Yeah. This is perspective projection. This is another example of perspective projection. So what is the difference in effect between orthographic projection and perspective projection? How would you, okay, if I show you two images, it has to go some kind of projection, right? How would you know if it's an orthographic projection or the perspective projection?
The parallel lines stay the same.
With
Orthographic projection.
With the orthographic projection, parallel lines stay parallel, right? And we could say that. Why? Because in orthographic projection, z is ignored. Okay, z is ignored. There is no z component in the resulting system. But with this one, you divide the things by z. If z is very large, then your x and y becomes very, very small, right? With this one, we don't have it. Okay, with this one, we don't have it. So that's one way to understand if the parallel lines are there or not. Okay, so there is a special lens that kind of produces the orthographic images. We call them telecentric lenses. Okay, look at the scene. Okay, if I do this, if I take this using a conventional perspective projection lens, this would be the image that I see, right? So what do you see? How do you know that this is a perspective projection? Salman, your thing doesn't work very well here, right? I mean, all the parallels are parallel again. I mean, this red, this part is parallel to this one is parallel to this, and blue, green is like that, right? And blue again. Parallels are parallel.
But their extensions will eventually meet, right?
What?
The lines you draw, when you put them up, they should eventually meet.
No, well, this is perfectly parallel. It is not going to intersect, right?
One of them should meet.
No, I mean, green, red, blue, they won't.
Then, okay.
Then what? Then what? You see something. Then how about what?
About the plane, maybe.
How about the black ones, right?
Yeah.
How about the black ones? Black ones are going to, even though they are parallel, I know that, right, this one, they are going to intersect, right? Parallel lines are going to intersect. So this is perspective. Well, I don't care about the parallel lines, but all I care is this. I know that in real world, the size of the red box and the blue box are the same, but on my image they are different. That's not good. If I am doing an inspection, if I am measuring their sizes, and if I like to know that if they are all each 5 millimeters high and 5 millimeters wide, then this is not used, right? I mean, my measurements depend on the length. But if I use a telecentric lens, this is what I am going to get. Okay? Doesn't matter how far your blue is, it will be the same size as the red. This is called telecentric lens. And can I click on this one? I like to show you one good example of from the telecentric lens pin inspection. Images. They are usually used for inspecting the yeah, this is good. Yes. Okay, this one. If I take, let's say, I have a VLSI chip. I have a VLSI chip like this one. And I like to find cases like this. See, this is bent. This is not in right angle to the board, okay? So if I take a picture of this chip using a perspective camera, this is what I'm going to get. Okay? The distance between the tops of these pins are larger and bottoms are smaller. So I cannot do much inspection, but if I use a orthographic projection lens or telecentric lens, this is what I'm going to see, and I can definitely find this. Okay, so with this for this kind of cases, okay, orthographic projection is important, and I can handle it because I know how to do orthographic projection. But usually this is our projection matrix. Given the three-dimensional position of a point, these will be the corresponding point on my image plane. Okay, any questions so far? Okay, if there are no questions, I will continue then. Let me skip this one. Okay, let's go back to our previous discussion. Let's go back to the formulas. Doesn't matter if I am using D or if my center of projection is in front of the image plane or not. Okay, any point x, y, z on the real world will be projected to x prime, y prime, and z prime on my image plane, pi prime. Okay, this is my image plane, pi prime. Good. Okay, so in this case, I actually don't like this. I mean, I don't want to talk about this z prime because z. What is z prime? Z prime is constant. What is its value? What is the value of z prime? Here. Okay, nobody answer me. No. Don't say anything. Don't say anything. I will pick somebody. Alper Balmumcu. Alper, what is the value of z prime?
So 1?
Is it 1? No, it is not. But I mean, why did you say 1? Because it's a normalized distance. Do you assume? No, it is not 1. You are close, but it is not 1. Look at the picture and you can tell me. What is the coordinate of pi prime? I mean, pi prime is this plane. X and y values change, but the z is constant. What is z?
I don't know.
I am not saying you should know. I am just asking you to look at the picture. It lies in the picture. It is in the picture. Okay, Arda, you tell me. Arda, Taha, Candan.
Is it minus z?
No. Well, z is, what did I say? This z prime is constant. When you say minus z, then it wouldn't be constant, right?
Yeah.
X prime and y prime are not constant. That's why I have formulas for them. But for z prime, I don't have a formula because it is constant. What is the value of z prime? Barış, can you tell me? Barış Şahin?
Can it be 0?
Well, if it is 0, then it would be here, right? This is 0, 0, 0. No, it is not 0. So maybe, Barış, can you tell me what is the position of C prime then? What is the position of C prime? Here.
F prime?
Well, it has 3 coordinates. It has 3 coordinates, right?
Yes, 0, 0 and F prime.
Exactly, 0, 0, F prime. So if C prime is 0, 0, F prime, what would be the Z prime of any point on that plane?
F prime.
F prime, exactly. So Z prime is F prime. This one, focal length. Okay. Since I am projecting these 3-dimensional points on this image plane, okay, 3-dimensional points on this image plane, I am going to lose one of the dimensions. Z is going to be lost. X and Y are going to change, and these are the formulas. And Z is going to be a constant. That's called that's why we call it projection. Okay, we lose one of the components. So we are losing a lot of data when we take pictures of the real world objects. Okay, and orthographic projection says that doesn't matter what your Z is, my X and Y, X prime and Y prime, okay, are going to stay the same. Perspective projection says that no, the position on your image plane of a point depends on their Z. Although I'm going to lose that Z information here, okay, the position of X and Y will depend on Z. Okay, so this F prime is very important for us. It will be very critical parameter of our camera, very critical parameter of our camera in determining this X prime and Y prime numbers. Okay, so another thing here is this. I like these two formulas, X prime and Y prime, but they are in millimeters. They are in real world coordinates. On an image, I like to talk about columns and rows, okay? If this is my image, okay, if this is my image, this is column number 1, column number 2, 3, 4, and this is row number 1, row number 2, 3, 4, 5. And if I like to talk about a point, I don't want to talk about 5.2 millimeters or something like that. I mean, this point for me, in the real world, it is 1.7 millimeters, 2.5 millimeters, and let's say our F is 100 and 100 millimeters minus 100. Okay, I don't care where this point lives in the real world. All I like to know is this point is on my image, fifth column and fifth row. That's it. X and Y. 1, 2, 3, 4. 1, 2, 3, 4, 5. Sorry, 4 and 5. Okay, because on my image, that's what I do. On my image, I care about my columns and my rows. So how do I? Okay, this one is produced by. Okay, this coordinate is produced by these two x prime y prime formulas. How am I gonna go from these numbers to this number? What do I need? I know that this is 0, 0, 0, right? And this one is here. This point is 0, 0 minus 100, right? I know that one too. So how would I go from this position to this one? Anybody has any ideas? It is not difficult. We need to know something here.
You know, the angle of P O C prime, P prime O and C prime.
It is just right angle. No, it is just right angle. I mean the angle between this x, optical x, and the pi prime is 90 degrees. I know that. What else do I need to know? How many rows are there in this image? Here. How many rows and how many columns are there? How would I know that? What is number?
From the sensor, right?
We need to know the range.
What do you mean, Arda, range? What is range? Just explain that.
I mean minimum and maximum values of x and y.
So what determines that? It is our sensor size, right?
Yeah.
What is our sensor size? Sensor size is important. That's one thing. The other thing is, what is the size of each? What is the height of each row? What is this height? H. Also, what is this width? W. Right? Each pixel should have a height and width, right? So I need that. And even though it's going to be very, very small, if I know that, okay, if I know that, by dividing this width with this number and height with this number, I can get the row and column of the pixel that this value belongs to. Okay, so these are very important parameters. One is the focal length, odak uzaklığı in Turkish. The other two is the width and the height of the pixels, sensors on my real CMOS sensor or the CCD sensor. Okay, these are the other two things. If I put them in my equations, it will be clearer. So there is a real world point. This point is projected through my pinhole. That's what my assumption is, even though I am using the lenses. Okay, this one will hit my physical retina or the sensor array. This one has many rows and many columns. Okay, and I know my focal length. My focal length is this much. This is my focal length. Okay, F. That's my focal length. Okay, so C0 is F away from 0. To make things a little bit more understandable, I will assume that there is a normalized image plane. Although I don't have such a physical plane at all, I am going to assume it. In this physical plane, okay, it is just 1.0 away from the origin, 1.0 away from the origin, and everything is perfect on this one. So since this one is 1.0 away from the origin, f I can assume that f is 1.0. Well, in this case, this p hat is going to be, let's say this one is x, y, and z. Since this is just 1.0 away, remember the formulas. X prime is x over z times f prime. Okay, so this is going to be just x over z p hat, right? Because f is 1.0. Oh, sorry, this is comma y over z. That's the coordinate. But such a plane does not exist. I like this plane because I assume that f is 1.0. But then this plane doesn't have rows and columns. So the p hat lives in the millimeter world. Okay, it doesn't talk about the rows and columns. This one is the real world actually. This one is the CCD sensor. This one is f away from the center of projection. Also, this one has rows and columns. Okay, rows and columns. So I will assume that I know the image pixel height and image pixel width. Okay, with this one, let's write a formula to get the x and y position of this point P. This point P corresponds to P prime, P hat. This is normalized image plane. This is physical CCD sensor. Okay, so this is the formula actually. U hat and V hat, it corresponds to my P hat. Okay, x over z and y over z. To get P hat, remember my point P, x, y, z, and I put a 1. This is in homogeneous coordinates. What is the size of this vector? What is the size of the vector that I framed with the blue line? Okay, Denizcan Erdem Yılmaz. Deniz, can you tell me the size of this vector? These questions are so simple, I think most of the people are kind of find it boring to answer maybe, but I have to ask. Denizcan, are you there? Okay, Denizcan, are you there? No.
Çete yazdı hocam.
I cannot read the chat. I don't see chat. Can I see it? No, I don't. If you don't have a microphone, Denizcan, you are not supposed to be on this lecture. So what is your answer? People, if you don't have a microphone, just don't attend the class then. So we are waiting for Denizcan to write something and somebody will read it.
he says size of the P1 vector is P square plus 1.
No. This is a very simple question. We don't have. Okay, Barış, can you tell me what is the size of this vector here?
P, I guess.
P is this. P is a vector xyz, right? If I put a 1 just underneath it, what would I get? 4-dimensional vector in homogeneous coordinates.
To multiply 4. Is that true?
Why do you multiply it with 2? P is a vector of size 3xyz, and I put a, okay, P is this, okay? If I do this P1, it means xyz1. 4-dimensional vector that represents 3-dimensional point in homogeneous coordinates. Okay? So don't think too complicated. I'm just trying to make you guys follow the lecture, okay? So this is a 4-dimensional vector.
I thought that ID and 0 multiply P and 1.
Oh, yeah. So you are trying to answer the whole question. Okay, I will come to that in a few minutes, Sheda. Yeah, that's good. Okay, somebody was asking a question.
So why John's answer is incorrect?
What did you ask again? Why what is incorrect?
John said P to the P square plus 1. Why is incorrect?
Because that is I don't why P, what is P square? P is a vector, right? 3-dimensional vector.
Yes, it's simple vector length calculation.
If I put a 1 under xyz, how would you calculate the size of this vector? You just add 1. What is P square? P square is P times P. So
All right, I'm mistaken. I understood.
So don't think this very complicated thing. Don't think this is a complicated question. It's just I am adding just 1. I am making this inhomogeneous coordinate a homogeneous coordinate. So what I am expecting you from, okay, what I'm expecting from you is you will say that we are making it an homogeneous coordinate. So it is just from 3 to 4. That's it. This is an identity matrix, and this is 0, 0. So this is a matrix. So tell me the size of this matrix now. Since this is 4-dimensional, right? This is 4-dimensional. It has to have 4 columns, right?
3.
It has to have 4 columns. So it's going to be 1, 1, 1, 0, 0, 0, 0, 0, 0, and all zeros here. Okay. And this is xyz1. So what did I do with this one? What I did is, it is just perspective projection. That's it. Perspective projection, like I did before. Perspective projection. Remember the perspective projection matrix here? Okay. Here. Okay. It was like it is exactly the same as this, right? 1, 1, 1, 0, 0, 0. But you will say that where is D? Well, since this is normalized image plane, Remember, we assume D is as 1.0, so D is gone. So what I get is, okay, this is 1 again. Okay, that's what I did. That's what I did. I am working on this still. I am still working on this. Okay, so 1 over Z, if I do the homogeneous to non-homogeneous system, I have to divide it with Z, and I will get P prime. This is what I get. Sorry, P hat. P hat has two components, U hat and V hat. The coordinates of P hat is X over Z and Y over Z. Okay, so this one we already know. Let's try to find how we go from P hat to P. P needs to be expressed in terms of image coordinates, row number and column number. P hat is in millimeters again, in real world coordinates. If this is 0, 0, 0 in terms of millimeters, okay, this is 0, 0, 0, 0, 1, and this is X over Z, Y over Z, comma, 1. Okay, we switched again the coordinate system. Z is growing this way. This is all positive. Okay, all the real world points are in the negative space. Okay, I'm trying to relate this one with this one. Okay, so I am going to introduce this. I need three things. One is this focal length, F. The other one is the height and the width of the height and the width of each pixel. This is my pixel, right? Three numbers are there. Okay, so the book says that I am going to use these three parameters, K, L, and F. K, L, N are the widths and the heights of the pixel. Instead of W and H, it uses K, L, N. Okay, but they say that K and L are not K, L, and F are not independent. They can be expressed in terms of each other. So I will drop them to, I will reduce them to two numbers, alpha and beta. K times F is alpha, L times F is beta. Okay, so the width of a pixel times focal length is alpha, focal length times height is beta. If I do that, to get the U and V from U hat and V hat, this would be the formula. X over Z times alpha, Y over Z times beta, then I have U0 and Y0, V0, sorry. Can you tell me what is U0 and V0? U0 and V0.
Is it focal length?
Focal length is F. And we factored F into alpha and beta. Remember, alpha is K times F, beta is L times F. What is U0 and V0?
Is it
Look at the picture here. Picture is important.
Maybe unit vectors.
If it is unit vector, then 1.1 and 1. No, it is not. Doesn't make much sense. Well, I mean, remember what did I say? I said that we need to factor into the width and height of the pixel measurements. That's fine. I did that, but then I introduced this U0 and V0. The thing is here. What is the point? What is the position of C0? C0 is 0, 0, F, right? That's the C0. Okay, so this is the origin of this plane, 0, 0, F. But the origin of my image is not in the center. Origin of my F is either here or there. I start from the corners, right? So the coordinate of C0 is important. I need to find, okay, the column number and the row number of this 0 in terms of pixels. So that column numbers U0 and V0 corresponds to the pixel coordinate of this image center. This is called the image center. So U0, okay, for me, for my image, what is 0, 0? 0, 0 is here, right? This is my column number 0, row number 0, right? But in terms of millimeters, in the real world coordinates, C0 is different. Okay, so I need to find the difference between these two. So this much. This is going to be my U0 and this is going to be my V0. Okay, that's called the image center, U0 and V0. So I have introduced two more parameters. For a given camera, I need to know the image center, U0 and V0, and I need to know alpha and beta. If I know those, then given the real world point x, y, and z, I multiply it with alpha and beta and add U0 and V0, and I would find U and V. Okay, so this would be the formula. Again, this is just a formula. This is not a linear matrix multiplication, but I'm going to show you how we do that in a few seconds. Okay, before we move on, there is another parameter that we don't use all the time. Okay, what is the angle between these two? Well, I kind of draw it, but what is the angle between U hat and V hat? 90 degrees. Yeah, they are orthogonal, right? It is 90 degrees. So what should be the angle between these two, U and V? I would expect it is to be 90 degrees, but in the real world, since this is a physical device, they cannot make perfect sensors. Okay, their rows and columns are not perfectly orthogonal each other. Instead of 90 degrees, perfect 90 degrees, sometimes it is 89.9 or 90.1 or something like that. Okay, so if I have such a difference, that's going to make lots of calculation errors, so I need to factor this one into my calculations. I am not going to go into details, but if you put that angle theta into the calculations, this is what U and V should be. There is a cotangent theta, there is a sine theta in the formulas. Again, how many parameters do I have now? With the green, 1, 2, 3, 4, and 5. 5 parameters. Okay, 5 parameters. This is image center. These two are image center. These two are pixel length and width, and this is the skew angle. Skew angle.
Don't we know V0 if we know mu 0?
No, because this one doesn't have to be a square sensor. Okay, this one doesn't have to be a square sensor. Okay. They are not equal. Okay, some sensors are like rectangular, some sensors are like square, like we wouldn't know that. Okay, so these are the parameters. If you like to know, if you know the position of x, y, z of your point, and if you like to know where that point projects to in your image, then you run these two formulas. But to run these formulas, you need to know alpha, beta, theta, U0, and V0. Where do I get these numbers? Where do I get these numbers?
Didn't we calculate it before?
Somebody has to calculate it, but maybe whoever constructs that camera, whoever produces that camera knows the f number, right? It knows the pixel width, pixel height, right? It knows the theta. Maybe they will give me those numbers, and I will use them in my calculations. But usually we don't do it that way. For each camera, we do calculate these numbers ourselves. Okay? We calculate these numbers, we estimate these numbers, these parameters ourselves, and we call this operation camera calibration. Okay? Camera calibration is the estimation of these numbers from the images, and we are going to talk about it in one of the lectures of our course. Okay, any questions so far?
I have a question.
Sure.
If the camera producers no theta angles, why don't they düzeltmiyorlar?
Make it 90 degrees.
Yes. Why don't they make it right?
Yeah. Well, sometimes you cannot. Sometimes you produce a product. You can measure the error, but you cannot make it perfect. Okay. Sometimes it happens.
After produce it, they saw the wrong angle.
After they produce it, they measure it and they realize that it is not perfectly 90 degrees, but 90.1, 90.01, etc. It is like, you know, this, we produce this F-16 fighter planes, right? After they produce each fighter plane, they measure its error. They say that it is 2% in error. So it is tolerable. Anything 95%, we can use it. Sometimes they produce perfect airplanes, okay, no error at all. So it becomes an actually event, okay. From the news, you would hear that this month they got one perfect airplane, etc. Producing something is different than measuring the error. It is easy to measure the error after you produce it. Okay, it's one thing, and it's producing the perfect thing. The other thing is this: even after they measure the theta angle, okay, even they measure the theta angle, it changes. When the CCD heats up during the operation, it deforms, and this angle changes. Okay, so if the environment is too cold, okay, if the environment is too hot, depending on where you are, depending on your casing, it changes. So it is better for you to estimate all of these parameters yourself before you use your camera every day. For some applications on the factory floor, they stop all the operations every few hours and they recalibrate their cameras. Okay, any other questions?
I have a question, sorry. Can we say we have an image and we change it to vector space and the image we saw in our computer or display, it depends on the plane where we put the plane in that space. Is it right?
Yeah, that's true. I'm going to talk about it in a few minutes. So you are saying that you are saying that we are ignoring where this point is with respect to camera, right? This point is in the real world. We assume that this is 0, 0, 0. But when I change my camera position, the relative distance between this P and O will change. How about this? Okay, this one assumes that camera is at the center of the real world. That's not true. Okay, so I will talk about it in a few minutes.
Okay.
That's a good point. Okay, let's take 10 minutes of break, and we will, when we come back, first we are going to make this a linear matrix multiplication, this calculation. So we are going to use whatever we know so far, homogeneous coordinates. Then we are going to talk about what Doha has asked. So let's be here around 1438. Okay, so let's continue from this point. We said that we have 5 parameters now. We need to estimate them, but before going on further, let's try to express these using a linear matrix operation like that one. Okay, and what we're going to do is we are going to place all these alpha, beta, theta, u0, v0 numbers inside these matrices, and we'll do it that way. Okay, so that's it. This matrix, okay, is called intrinsic parameters matrix. Intrinsic, in Turkish, içsel kamera parametreleri matrix, and it's a 3 by 3 matrix. Okay, so before that we said that it is 3 by 4, right? 3 by 4, but that was working on the real world coordinates. This one works on p hat. So whatever p hat we have, multiply it with this k matrix. Okay, k matrix, and we are gonna find this point P. Okay, so what we have here is something that transforms our coordinates from this plane to that plane. Okay, so it is already working on homogeneous coordinates, of course, but it is working with 2-dimensional homogeneous coordinates. Okay, that's why it is 3-dimensional vector. Okay, let's look at this one. Let's look at this one. This one says alpha is beta. Let's for a moment, let's ignore this theta. Let's say theta is perfect, it is 90 degrees. And in that case, k would be alpha. What is the cotangent of 90? What is the cotangent of 90?
It's 1.
Is it 1 or
0.
0? Okay, it is 0. So it is u0, 0, beta, and this is v0. Sorry for my v. Oh, okay. So this is 1, 0, 0. So how is this different from the identity matrix? It is like identity matrix, but we put u0 and v0 here, and instead of 1 I have alpha and beta. Okay, and then then we are only interested in transforming a real world xyz to the image coordinate system. How are we gonna do that? This is how we are gonna do that. I will define a matrix M. Matrix M, as previously, is a 3 by 4 matrix. The first part is 3 by 3 is k. This is 0. So if I ignore this theta again, M would be, by definition, alpha 0, u0, 0, beta, v0, 0, 0, 1, and this is 0, 0, 0. So if I multiply this with any x, y, z, 1, okay, if I multiply it with any x, y, z, 1, okay, this would be like, this is m, this is p. This would be like m times p. And this is going to give me the homogeneous coordinate, corresponding homogeneous coordinate on my image. And I divide it by z to get the 2-dimensional inhomogeneous coordinate corresponding point. Okay, so now I can use all these camera parameters to calculate my image coordinate system. But still, as Doğa said before, I assume that this P lives in the coordinate system or of this camera. Camera thinks that my center of projection is 0, 0, 0. Okay, let's say, suppose this is, let's say, okay, this is my camera right here. This camera is looking at the real world, This camera is looking at the real world, and the 0, 0 is the projection of this camera. Okay, I know that. I took the images, but if I change the position of this camera, I change my 0, 0, 0, but the real world objects doesn't change, right? So how is going to happen? How am I gonna put this into consideration? So I need to find a way to relate camera coordinate 0, 0, 0 with the real world coordinate. Let's say the real world coordinate starts some position 0, 0, 0, and I like to express the difference between the camera 0, 0, 0 and the real world 0, 0, 0 so that I can relate my camera position to the real world position. That's what we're going to do right now. Okay, so don't forget this one. M is K0. It's like this one. This is very similar, like what we did before, identity. Where did I put that one? Where is that? Oh, it was coming later, right? So where is it? Yeah, this identity 1, 1, 0, 0. Okay, now instead of identity, I would put alpha here, beta here, U0 and V0 here. If I ignore the theta. If you don't ignore the theta, this one and this one changes too. Okay, so let's talk about the difference between the camera coordinate system and the real world coordinate system. Okay, so I am going to define a transformation between this is what we are going to do. Okay, let me draw it here. It's like this. This is my camera. It is looking at the real world, and this is my coordinate system inside my camera. Okay, X, Y, and Z. In my real world, there is a point P, and the XYZ of the real world is like that. So this is 0, 0, 0 of the real world coordinates, and this is the 0, 0, 0 of the camera itself. I like to know the relationship between this point and that point. So the difference between them. Doa, can you turn off your microphone? I am getting some hissing noise. Okay. So I like to relate these two in a way that I know. I mean, if this P is expressed in terms of camera coordinate system, and I know the relationship between this coordinate system and this coordinate system. This is my camera coordinate system. This is my this is my real world coordinate system, and this is the camera coordinate system. If I know the relationship between these two, then I can relate this point which is expressed in the real world system in terms of camera. Then I would continue. That's what I'm going to do. Okay. So before doing that, I will give you some geometric information. Okay. When you talk about XYZ, we use the right hand rule. Right hand rule, something like that. You do your You do it. Okay. If this is your I, J, K, X, Y, Z. Okay. Use your right thumb. Okay. To show the direction of your Z or K. And if you do this this operation here, this movement, you are wrapping your fingers around this Z-axis. You should first meet X then Y. So this you have a right-handed coordinate system. So most of the time we are going to use right-handed coordinate system. That's the regular coordinate system. But if you like to use the left-handed coordinate system, sometimes it happens. It is just the opposite. So right-handed coordinate system. This is a right-handed coordinate system, X, Y, and Z. Okay. So with the right-handed coordinate system, let's say A is my camera coordinate system and B is my real-world coordinate system. I have IJK again. Okay. If a point is expressed, point P, there is a point P. If this point is expressed in terms of A coordinate system, how do I express the same point in terms of B coordinate system? Okay, if there is only pure translation between these two coordinate systems. See, KA and KB are the same direction. Okay, JA and JB are the same direction. IA and IB are the same direction. So their directions are exactly the same. There is no rotation between these two coordinate systems. Only translation, there is translation between them. So this formula says that if P is expressed in A, okay, just add this vector. This vector is the difference between these two coordinate systems. Just add this vector to PA, okay, then you will express your point in B. That's it. So I need to know how many parameters do I need to know to make this transformation? What do I need to know? How many numbers do I need to know to make this transformation?
3.
Just 3, right? So what is 3? It is just the x, y, z components of this vector. That's it. 3 numbers would be enough. Okay, 3 numbers would be enough to make this translation transformation. So that's one thing. The other thing is there might be a rotation between these two. I assume that there is no rotation. So if there is a rotation between these two coordinate system, remember red is A, green is B. They don't have any translation difference, but they have rotation difference between them. But in that case, you need to multiply a point AP. P is expressed in terms of A coordinate system. You need to multiply that A with a rotation matrix. This rotation matrix will transform this point from A coordinate system to B coordinate system. So this is a 3 by 3 matrix. Okay, so this is a 3 by 3 matrix, special rotation matrix, and this 3 by 3 rotation matrix by definition is orthogonal matrix. That means that R transpose times R is identity. Also, I mean, what does that mean? If R transpose times R is identity, then that means that I transpose is equal to what? R
Inverse.
just the inverse, right? R minus 1. So these kind of matrices are called orthogonal matrices. Okay, orthogonal matrices. So question, you told me that 3 numbers are just enough to express this pure translation transformation, right? How many numbers do I need to express this pure rotation case? How many numbers do I need to express this? It looks like I need a 3 by 3 matrix, right? It looks like 9 numbers, but it is much lower than 9. It is not 9.
Six maybe.
No, it is lower than 6. Where did you get 6? Well, all I need to know is what is the angle difference between the x coordinate system, what is the difference between this KA and IAE, like this, sorry, KA and KB. Yeah, okay, here it is. What is this angle? That's one thing. Okay, so that's the difference between the K components of these three coordinates, right? How about the difference between the J components? J components are like that, so this angle. And then how about the difference between the I components? So IB and IA, so that would be the third one. So 3 numbers are enough. So why do I need this 9 numbers? So if I put it in 9 number case, this operation becomes a linear operation. With a simple matrix multiplication, I can do that. With a simple matrix multiplication, I can do that. So this is good. But this is not good. This is addition. Addition is not good because addition is not linear. Okay? I need multiplication. I need multiplication. So one of the advantages of using homogeneous coordinate system is that this addition can be expressed in terms of multiplication with the homogeneous coordinate system, and I'm going to show you in a few minutes. Okay, so by the way, just to express it in a more simpler way, for two-dimensional world, let's say I have this on a simple plane, okay? I have only I and J components, X and Y, that's it, okay? If I like to transform a point from this red coordinate system to green coordinate system, the only difference is this angle, right? The angle is different. So if I'm looking from top, so what do? There is only one parameter, that's just one parameter, this is the theta angle theta. Okay, so how do I use this? So this is how you convert that information to this 2 by 2 matrix, because in this case I have just two-dimensional world. Okay, in two-dimensional world this transformation is just 2 by 2 matrix, but there is only one number in this matrix, it is just theta. All the rest are derived from this theta. Okay, so this is just one example. See, this one is orthogonal matrix. If I multiply this with transpose of it, it is cosine times cosine square, right? And then cosine times cosine theta sine theta, and it's going to be 0. It's going to be 1 at the diagonals, and it's going to be 0 at the other ends of the matrix. So it is orthogonal. Okay, good. So this is the general case. I have two coordinate system. There is rotation difference and there is translation difference. So what do? I take this point P, I rotate it, and I add this vector. Rotation first, then addition of the vector. But again, this is not a linear stuff. I need a nice linear operation to transform this point from one word to another word. Okay, and then of course I have the homogeneous coordinate system. This is what I am going to do. Okay, I will put a 1 under this P, so it is going to be a 4-dimensional homogeneous coordinate system. Okay, and I will multiply it with this transformation matrix, and I will get another 4-dimensional homogeneous coordinate system. So what is the size of this T? Can somebody tell me? What is the size of T? It's a matrix, right?
Four times 4?
It is 4 by 4, right? 4 by 4. Why? Because this one has 4 elements and this one has 4 elements, so it has to be 4 by 4. And this is the definition of that matrix. Okay, how could this be a 4-dimensional? Why? Because this is 3 by 3, right? 3 by 3. This is all zeros, 0, 0, 0. and this is just 3 elements. This is 1. So 4 by 4 matrix multiplied by this homogeneous coordinate point, 4-dimensional point, and I will get another homogeneous coordinate in 4-dimensional world. Okay, so instead of doing addition and multiplication, I just express this thing in a single matrix multiplication, which is perfect. That's what I want, actually. That's what I want. So how does this happen? This happens like, okay, this happens like that. Rotation, translation, 1 and 0. How does it work? So rotation is multiplied by this one. So it is trying to say that if you do this multiplication, this is what you get, and it's same as this one. R times P, okay, T times 1, and if you add them together, you would get the P prime. That's because I am adding this one here, okay? So instead of using an addition, I express everything in homogeneous coordinates, and I don't have any addition anymore. Everything is expressed in terms of multiplications. Everything is linear. Actually, this is the major, maybe the most important reason why we switch to homogeneous coordinate system, because with homogeneous coordinate systems, all the things can be expressed in terms of matrix multiplication. Okay. Good. Any questions so far? Okay, so but I didn't talk about the all we did is I expressed this P, okay, in A. I know that. Yeah, let's say this is our real world coordinate system. Okay, I know the position of this P in real world coordinate system, and I like to express this in camera coordinate system. So this is what I do. So I take this P A and I multiply it with this 4 by 4 matrix R T 1 0, and I would get PB. Okay, so I have, let's say this is real world coordinate system and this is a camera coordinate system. Still, my point is in 3-dimensional world. I did not express it in image coordinate system. So how do I express this in image coordinate system? I would take PC and I multiply it with this M. Remember M? We have M, right? M is our intrinsic camera matrix. Okay, and remember, if I do that, that would give me my small p image coordinate system. So I am going to combine this matrix with this M, and I'm going to get one large matrix, and that's going to be my projection matrix. That's what we are going to do. Okay, this is the formula actually. R is the rotation matrix, T is the translation vector. So these two are for relating the real world coordinate system to the camera coordinate system. Okay, so there are 3 numbers in it. Although this is a 3 by 3 matrix, there are 3 numbers in it. So 6 numbers come from the rotation and translation, and this is my intrinsic camera parameters. And if I multiply these two, I would get my projection matrix. Any point in the real world coordinate system multiplied by M will be my image coordinate. If I divide it by Z, I will get the non-homogeneous point. Okay, so this is the matrix. K is a 3 by 3 matrix, R is a 3 by 3 matrix, T is just a three-dimensional point. Okay, three-dimensional point. And if I express everything in terms of matrix calculations, this is the matrix M, which looks complicated, but let's look at it. So this TZ is the third component of the translation vector. So this is this a vector or is this a scalar? Is this a vector or is this a scalar?
Should be scalar, right?
It's a scalar, right? Because it is the third component of the translation vector, right?
Yeah.
How about this one? This is the third row of the rotation matrix. Okay. So it is a three-dimensional. It is three numbers. So this one is just one number, two number, three numbers, and this is just a single number. And again, this is a scalar again. Again, another scalar. And this is a row vector, row vector. So M is a 3 by 4 matrix. M is a 3 by 4 matrix. 3 rows, 4 columns, which we call a projection matrix. Okay. M is a projection matrix. Given a point P in the real world, in homogeneous coordinate system, if I multiply P with M, I would get the corresponding point on my image plane as in homogeneous coordinate system. So I have been working on this for the last 2 weeks. Finally, I am showing you what I get. So this one includes lots of data actually. How many parameters are there? Let's look at this one. How many parameters are there? Let's count it. Okay. The elements of the translation vector 1, 2, and 3. Okay. These are the translation vector, and for my rotation matrix, okay, although there are three rows, each one includes 3 numbers, I consider it as a 3 number, okay. So for the translation there are 3, for the rotation there are 3, then I have my intrinsic parameters, which are beta, alpha, theta, and u0 and v0. And for the intrinsics, I have 5 numbers. So total of 11 numbers. Total of 11 numbers determine this matrix M, projection matrix M. How many numbers are there in M? There are 12 numbers, right? Because it is a 3 by 4 matrix, but to make this M, I need these 11 numbers. If you know these 11 numbers, then you did your camera calibration. Okay? These rotation and translation components of the camera parameters are called extrinsic camera parameters. Okay? These are extrinsic camera parameters. Dışsal kamera parametreleri. Extrinsic camera parameters change whenever you change your camera position. Where is my picture? Camera picture. Okay, here. Okay, here it is. Okay. If I move my camera, okay, or maybe I can do this. If I change my camera position from this position to that position, Okay, now I have to come up with another RNT. So this is R2 T2 and this is R1 T1. But when I change my camera position, my camera intrinsic parameters doesn't change. My camera intrinsic parameters don't change. Only the extrinsic parameters change. So out of those 11 numbers, 6 of them change. 5 of them stay the same. Okay. So in fact, when you say I have calibrated my camera, it usually means that you found out that those 5 numbers: alpha, beta, theta, U0, and V0. Okay? So you have been so quiet. Can I have some questions? Get this out, like here. Of course, I am not expecting you to memorize all this stuff. But you should know this. M is KRT. K is 3 by 3. R is 3 by 3. This is 3-dimensional. Okay. Total of M is 3 by 4. K is our intrinsic parameters, extrinsic and extrinsic. Okay, any questions? If nobody has any questions, I will force Doğa to ask me a question. Okay, Sam. Okay.
So we said that the rotation matrix was an orthogonal matrix.
Yeah.
So if we reduce an orthogonal matrix, will it have the rank of 3? Can we reduce to it such that it will have only 3 numbers that are important?
Yeah. But it is not a full matrix, of course. I mean, R is not a full matrix. Okay, it is only a rotation matrix, and we are going to take advantage of this R. Okay, a lot.
Okay.
It is not
that property comes from the matrix being orthogonal, right?
Yeah.
Okay.
But it's by definition has to be orthogonal. And when we recover, what is the camera calibration? Calibration means that we are going to recover all those numbers from the images. When we recover R, okay, we will assume that its rank is not full. Its rank is 2. So we should find a matrix whose rank is just 2. If you find a matrix whose rank is 3, then you are doing something bad. So there should be one way of enforcing this constraint.
Okay. Thank you.
By the way, if M1 is your projection matrix, okay, then let's say K is a scalar number, okay. Since this is in homogeneous coordinates, K times P is in the same point, right? It's the same thing. I can do that. So I can multiply K with I can multiply M with K. It is still my same projection matrix. Okay, so that's why M, the degree of freedom of M is not 12, even though there are 12 numbers in it. It is 11. Okay, good. Let me open up. Okay, this is good. This is from some other source. It's a good source, okay. So we are saying is that I have a real world coordinate system. I have a real world point which is expressed in real world coordinate system, x, y, z, 1 in homogeneous coordinates. I multiply it with a 3 by 4 matrix and I get this s, x, s, y, s in homogeneous coordinate system. And if I divide everything by s, then I would get my points. in homogeneous coordinate system. And I can decompose this to a 3 by 4 matrix into intrinsic parameters, okay, and the extrinsic parameters. But some people like to express it this way. They say that, okay, intrinsic parameters without the skew angle, f as x, remember alpha, the definition of alpha was this, right? Sx is the width of the pixel, sensor pixel. Sy is the height, and if I multiply them with f, then I would get alpha and beta. These are the center point, u0, v0. This is for projection. Remember how we did the projection? This is the projection matrix. And this is by 4 by 4 matrix for the rotation. And this is the 4 by 4 matrix for the translation. Okay. Identity 0, 1, translation. Rotation 0, 0, 1. Translation, rotation, projection, and intersects. So this makes the whole matrix pi or M. Okay. The definition of these parameters are not completely standardized. Okay. It changes. Some people like to include this theta, some people don't like it. Okay. It makes it a little bit crowded and scary, but it is not actually. Okay. Good. So let me open up the OpenCV documentation regarding the camera calibration and that kind of stuff. Camera calibration. Well, no, I don't want to. Am I opening? Okay, good. So this is how you do the camera calibration. You print out a checkerboard image like that. Okay, you print out a checkerboard image like that, and you show this image to your camera in many different positions and angles. Okay, so once you do that, okay, you get lots of data, and you detect these corner points using the corner detection algorithms of OpenCV. Okay, you get from all the images, and then you get your camera matrix using the let me show you. Where is it? Yeah, calibrate camera function. You get your points, okay, image points, and it says that, okay, this is your matrix, this is your translation vector, okay, this is your rotation vector. I will talk about these distortions in a few minutes, and this is your intrinsic camera matrix. Okay, and I don't know what a return is. I think it is some kind of a status. Let's go to the function itself. Let's get the documentation. Okay. Yes, calibrate camera. This one. Where is the documentation for calibrate? Okay, here it is. So return value, camera matrix. Camera matrix is the intrinsic matrix, rotation vector, and the translation vector. R vec, T vec, distortion. Where is returned object, return value, flags? Did you see it? Return value.
I think it returns the error.
Yeah, I like to know what kind of error.
It's on the downside.
Did you say it?
Yeah, after the parameters.
After the parameters. Returns, yeah, the RMS error. Oh, okay, so it is running some kind of an optimization. If everything comes back at 0, it is perfectly optimal. If it is not, then you are going to get some value. That's the return value. Okay, so this is the camera matrix. See, inside the camera matrix, this is what you have: fx, fy, cx, and cy. This fx and fy are not actually focal length in millimeters. I mean, there is only one focal length, right? There is no x focal length and y focal length. fx and fy are the pixel sizes in terms of focal length. Okay? Pixel size in terms of focal length. Cx and cy are the center positions. Okay? This is how you do the camera calibration. It is very convenient. It used to be very, very difficult, like 20 years ago. No, 25 years ago it used to be difficult. 20 years ago it became easy with this approach. This approach, I mean, this way of calibrating camera is difficult to explain a little bit, but it is very easy to use. There is another method which is easy to explain but difficult to use. Since we like the easy stuff, for me, I am going to show you how to do the camera calibration in a easy way but difficult to use way, but I am not going to ask you to do the camera calibration with that method. Okay, let me go back to my slides and continue from that point. But it looks like again I am out of time. Do you have any questions? Do you have any questions? Question for you. I think I asked this question, but I love asking the same question over and over again. Let's say I have a camera. I have a camera, blue camera. Okay, it is looking at the real world, and there is a point A and there is a point B. Okay, this camera is producing these images, A and B, small a, small b. Let's say I know the projection matrix M of this camera. So what do? I will say A is equal to M times A, B is equal to M times B, right? I can do that. I know my projection matrix. Okay. If I take the inverse of this projection matrix, so this is in three-dimensional world, this is in two-dimensional world, right? Okay. If I take the inverse of projection matrix A, that would give me capital A, right? So by looking at the two-dimensional point, I can get back to the three-dimensional point that produced this point, right? Can I do this? So that's kind of using this linear algebra stuff. I can determine the depths of points. From their image representations. Is this a nice property of this matrix, projection matrix? Tell me what you think.
Probably it won't be right because we lost one dimension.
Yeah.
And we projected the real image.
Yeah. What you are saying is very true, Rasul, but how could you explain this then? I am using the linear operations. I can write the inverse of a matrix and I can do this multiplication, right? My equations are telling me that I could do this.
Is M invertible?
Yes. I can find an invert. Yes.
We should be able to do this then.
Well, you should be able to. The equations allow it, but what Resul is saying is true. I mean, this is
But we have the-
projection. Projection. We lost one of the dimensions. How can you get the point back from some lost information? Suppose A and B are like this. Their
But we have the camera.
beam is just at the same point. I mean, doesn't matter if it's A or B. They are producing the same. Okay, let me change this picture. They are producing exactly the same point, right? So how would this equation know the difference between A and B? So what is this equation then? I mean, this is some kind of equation. I know that M is invertible at least to some degree with the pseudo inversion or something. I can write this, but I know that I am not going to get A, because if I am going to get A, then this would be B, but I know that A and B are the same point on my image. So what does this equation give me? What is M inverse times A or M inverse times B? What are these? I think it should be very clear from the picture. Look at the picture. What is this equation? What is this equation? Or what is this formula? It is the formula for this line. Okay? Same thing here. It doesn't give me a single point, it gives me a line. That line contains infinitely many points that can produce this point here. So it's not going to give me the perfect point with a depth, but it's going to give me a line along which infinitely many points live. Okay? That's nice. Good? Say yes.
Yes, it's now a little bit clear for me.
Okay, good. Okay, let's take 10 minutes of break. After the break, we will continue, and I will continue a little bit about this, and I will do this actually. Let me do this. Okay, let me do this so that another camera. Okay, let's say this is M1, this is going to be M2, and it is looking at this A and B, right? We are going to look at this when we come back. So let's be here around 15:38. Okay, people, let's look at this image again. So if this is my image plane in this camera M2, okay, the points of A and B will be on different positions. They will not be on the same position, right? So if I update these equations, this is M1 inverse, M1 inverse, okay. Okay, this is what I expect. These will produce a line, the same line, but if I do this M2 inverse times, let's make this A1 and B1, because this is A1, B1, and here is going to be A and B, A and B, A2, B2, okay? And if I do this M2 times A2 and M2 times B2, and these will be the same, right? Okay, so that means this is another line. Come on. This is another line. This line corresponds to the green line here. This one corresponds to the red line there. So if I intersect these two lines, then I am going to find the position of A and B, if I like. Okay, so if you have the images of, if you have two images of the same real world scene from two different angles, then it is possible to recover depth of a point if you know where the points are on your images. Okay, so usually we do it this way. Point A, what is going on now? Okay, point A times M1 is equal to A1, and point A times M2 is equal to A2, right? What do I know in these two equations? I know all these 12 numbers. I know all these 12 numbers. I know these three numbers. I know these three numbers. What I don't know is the three numbers in this A, right? Three numbers in this A. Then I can make this one large linear equation and solve for this A. Okay, so this is not exactly making a stereo system, but it is close. So it is multi-view geometry, multi-view camera systems, and we will do lots of stuff like that later in the semester. Okay, it is not possible to recover the depth from a single image, but if you have more than one image of the same scene, then yes, it is possible. Okay, let me continue. Okay, so OpenCV has lots of nice functions. The function for camera calibration I showed you. Another nice function of OpenCV is this project points. It's very good. Okay, let's say you have points, you have two-dimensional points expressed in homogeneous coordinate system. Okay, you have two-dimensional points expressed in homogeneous coordinate system, and you give your rotation vector, translation vector, camera matrix, distortion coefficient. We are going to talk about it. Okay, and these will be your inputs. This part will be your inputs, all of them. Okay. If you give them to your project points function, and it will take these points. These points are like your points P. Okay, these are your P. Get rid of this one. And these are your M, and this will be, and this will be your outputs, small p. Okay, this will calculate and will give you the results, project points. Okay, another good OpenCV function is find homography. You will say that I have two images. On image number 1, my source points. On image number 2, my destination points. Okay, and find me the homography, that is 3 by 3 matrix that connects these two images together, assuming that these are on the same plane. Okay, so please study OpenCV documentation. Try to see what kind of functions available for homography, finding the homography, calibrating your cameras, doing the projections, and etc. Okay, so I kept saying that I will talk about these distortions. Let's talk about the distortions. We said that on a projectivity, lines in one world stays as lines. Okay, if this is real world, okay, I have lines like those, and this is my camera. It is looking at the real world like that. On my image I produced, those two parallel lines could intersect. It could behave like that, but they will stay as lines. What the projection matrix does. Okay, this projection operation, okay, doesn't change the lines into something else. That's what I assume. But unfortunately, the lenses that we use don't produce images like this. Okay, the lenses that we use produce images in the center. Maybe the lines stay as lines, but when you get away from the center, for example here, this is a very nice line with the green. This is a nice line. This is a nice line. But when you get away from the center, things become either like that, pincushion distortion, or they become like that, barrel distortion. Okay, I mean, it should be like this dashed line, but it is becoming this like pincushion line. This is called the lens distortion. We cannot make perfect lenses. Lenses behave like that. Okay, especially the zoom lenses, cheap lenses. They change the picture a lot. So, and that's going to mess up all of my calculations of m times p, because I assume that everything is linear. Lines stay as lines, and circles stay as circles, and etc. No, it doesn't work that way. Sorry, circles doesn't stay as circles. Sorry, lines stay as lines. Linearity will be there. Okay, so it's caused by imperfect lenses, and the deviations becomes more pronounced at the corners of the images. Actually, at the corners they are even worse. So what are we going to do? We are going to find the distortion amounts, and we are going to undistort our images. So if my image is like that or like that, we will undistort them into this shape, and then we will run everything like that. So if you realize that the distortion is not there at the center, there is no problem at the center. When you get away from the center, distortion becomes apparent. So I am going to measure this. how far I am away from the center. This D is important. If D is 0, there is no distortion. But if D is large, then loss of distortion. So the distortion amount here is this much. Distortion amount here is this much. It has to be here, but it is here, right? At the center, there is no distortion. I need to find something like that. So I am going to modify it with, I am going to model it with radial distortion. So radially, no distortion around here. When the radius gets larger, distortion becomes larger. Okay, so I am going to measure how far I am from the center. If I am too far away, then distortion is going to be large. And they came up with this formula. Okay, this is a good example. This is a distorted image. Is this a pincushion distortion or radial distortion? Pincushion or radial? Sorry, pincushion or barrel? Which one?
It's
The
barrel.
barrel distortion.
It is barrel distortion. Barrel is like a barrel. You know the barrels? This is a barrel, right? So it is a object like that. You put your liquids in it, barrel. Okay, so this is a barrel distortion, and I like to convert this barrel distortion and get rid of it and get the linear image. So see, all the lines are lines. This is a line. This is a line. It is a line, right? In this case, no, these are not lines. It's a barrel distortion. Which one do you like better? Which one do you like better? Well, in terms of using our equations, this is better, but some people prefer this one. Can you tell me why they prefer this one? They say that this one is better.
Because of focus in the center.
Well, I mean, I produced this image from this one, so there should not be any focus difference between these two. I am not changing any focus. If it is sharp in this image, it's going to be sharp here. If it is blurred, it is going to be blurred here.
Center of the image takes more space.
This one takes more space. Just make it smaller.
The upper one.
This one takes more space.
Yeah, the center of the image.
Oh, yeah. So you like it better in that case. Center of the image takes more space. So you can focus it. Yeah, kind of maybe. Well, usually the idea is this. If I look at this part of the image, can I say it? This is a 90-degree corner, right? This looks more natural than this one. This doesn't look natural. So this the one that is distorted radially looks more natural locally. Okay? Locally it is more acceptable. Okay? Only locally. So circles look like more circles. If you look at it from a distance, that's not good. But for example, this one. But if you look at the other one, it looks weird at some point, especially at the end of the image, like these areas. Okay, so some people might prefer these kind of images. Okay, so let's go back and let's try to see how we can get this image out of the distorted image. It's called distortion elimination, modeling distortion. First, okay, this is our projection. X hat over Z hat. Okay, we know this is very simple projection. And Then apply radial distortion. Radial distortion is this. Find the distance between this point and the center, and that r square is going to be important. I am going to multiply r square with k1 and k2, kappa 1, kappa 2, whatever. Okay, so this is the square of the r, and this is the fourth power of the r. Add 1 and multiply with xn. That's going to give me my new position, undistorted position. And after that, if I apply f to that one, I would get the I would get the normalized image coordinates representation of the same point. So modeling the distortion means that finding this kappa 1 and kappa 2. And if I like to continue, actually maybe I can do k times r to the power 6. Okay. So once you find all those numbers, you can, there is an undistorted image function of the OpenCV. You would get this image, and now after that, you would calibrate your camera using this image. Okay. So 2 more parameters, intrinsic parameters for your camera. Okay. So that distortion stuff here means that I am going to give you the distortion coefficients, and you are going to use that in the projection operation. If we go to the camera calibration routines again, okay, remember the calibrate camera stuff. Yeah, here it is. This one gives you, okay, camera matrix, which is the intrinsic parameters, distortion coefficients, rotation vector, translation vector, etc. Okay, so OpenCV has a nice way of getting rid of these distortions. Usually we don't prefer this kind of stuff. We try to use good lenses that don't introduce any distortion. That's what we try to do. Okay, good. Well, other type of projection at the end of this chapter, maybe. Well, there are infinitely many types of cameras actually that you can come up with. Let's look at some of them. Somebody has this idea. Okay, this is your normal lens. Lens is looking upwards. Lens is looking upwards. Okay, this is a lens. Somebody has mounted this mirror on top of this lens. This is a hyperbolic mirror. So this is here, here. I'm trying to fix my pen. Okay, reboot the pen. This is a hyperbolic surface mirror. See that one? So when this lens looks upward, okay, if I have a picture, okay, this one, it will see like that, okay, this one will be like that. Okay, so this one is seeing all around this camera like this. Okay, it is seeing whatever it has around it. So it is seeing like 360 degrees. In the center it is broken. Why? Because in the center I have this post, okay, that supporting bar in there, but around it I have it. Okay, so this is called 360 degree field of view camera. and there are many versions of it. So you are seeing all around yourself, and usually autonomous vehicles they use this kind of images. Okay, another one is tilt shift camera. Okay, with the tilt shift camera, this is what you do, right? Do you remember the image that I showed you to give you the idea about the depth of focus? Let me go to that picture actually. Let me show you the depth of focus thing. Where is my depth? Remember those flowers? Flowers. Where did the flowers go? Yeah, here it is. Okay. So suppose this image plane is tilted a little bit like this. Okay. If this image plane is tilted like that, this point here, this blue point, will be in focus like that, but this green point here will not be in focus because this green point will appear here and that will be blurry, right? But here this red point will be in focus. So the focus area will be something like this. Okay. So this is what tilt shift lenses do. Okay. By tilting the lens, shifting the lens, you get different kinds of effects. Okay, this is one of the effects. So this is a real image. This is not a image of a toy city. This is a real city. But if you use this tilt shift effect, it looks like a toy image. Again, here another one. Or I think this one is a toy, or I don't know. I am doubting myself now. But definitely these are tilt shift effects. Okay, another sensor is this. Can you tell me what they did? Can you tell me how they took this picture of this cup or the cylindrical structure?
Stitching?
Well, kind of, but it is not the regular classical stitching. It is something else. But the idea is the same. The cameras that we use so far are three-dimensional cameras, right? They look at the three-dimensional world and they produce two-dimensional images. How about this? I have a camera. How should I draw it? Okay. This is my image plane. This is my image plane. Okay. Or maybe the other way. This is my image plane. And in the real world, let's say I have a circle like that. The central projection, the circle will appear like that, right? This is an image plane. But let's say I am using only the center column of this image plane. Okay, just a single column. I am ignoring the rest. I am ignoring the rest. So my images are just one-dimensional. So I am looking at two-dimensional world. I am producing one-dimensional image. Okay, so my lens is not like spherical lens. It's like a planar lens. You may take it that way. Okay, so what I am doing here is I take such a camera. By the way, scanners work like this. On a scanner, you have a sensor that has only one line of light sensitive elements. It's not two-dimensional. On your scanners, you don't have two-dimensional sensors. You have a single-dimensional sensor, okay? And you move your camera on top of your scanned document, and you stitch them together as Doğa said, okay? You move your camera on top of your scanner, the scanned document, and whatever you get, you put them together, and it becomes a two-dimensional image. That's how the scanners work. Okay, that's why the scanners have very high resolution. Why? Because they don't have like 1000 by 1000 sensors. They have 4000 by 1 sensor. Okay, and if you take the image of the document by moving the sensor maybe 5000 times, so it produces 4000 by 5000 image at the end. This one is doing the same. So if you rotate this object in front of a one-dimensional camera, it's not two-dimensional but one-dimensional camera, and if you stitch them together, this is what you get. Okay, so it's a specialized scanner, you might say. Okay, good. And one final and very interesting camera is the photo finish camera. Photo finish cameras are very old. In fact, they are invented at the beginning of the 1900s for horse races, photo finish horse races, and still we are using them to find the who has finished the race first and what are their times. And this is an example. This is very similar to this one, but of course the application is different. Again, this is like a scanner camera. It is taking one-dimensional images. Okay, let's say this is your track, running track. Okay, people are running in these lanes. Okay, and I have a camera here looking at the finish line. Okay, but this camera takes only one-dimensional images. Okay, if this place is empty, nobody is running, what kind of image would you get? Okay, this is the image that I would get. It would be all lines, right? Because it is all taking the same image over and over again. And if I put them together, I would get the lines, right? But if people are running at the position where I took the image, at the time position where I took the image, if I see a runner, I would record that image, and that image would appear here, and for the second person it would appear here, and the third person it would happen here. So time is going that way, and what is happening. That's why this looks funny. Okay, nobody has hands like that. Okay, nobody has a left leg this thick and right leg this thin, right? Look at these ankles, because these are all taken, each column of this image is taken at a different time. Okay, So this column here is taken at 21.8 second, and this column is taken at 22.8.3, sorry. So there is more than 1.5 second difference between these two. Okay, so this is photo finishing. Well, I said that beginning of 1900s this was invented, right? So, but we didn't have the digital cameras then. They used to use this, they used to do this with the film cameras. Okay, so one-dimensional cameras. So they are moving the film all the time, and they are getting these kind of images. By the way, nowadays they are selling one-dimensional cameras a lot. They are called scan cameras. Okay, it's not area scan but line scan. Let me put line scan cameras. Okay, line scan cameras are industrial cameras. They are used for inspecting. Okay, here it is. It's a very nice image. So this is the sensor. This is the sensor of the line scan camera. See, at the center there is only a single line. I don't have a two-dimensional image, and this one shows it very nicely. So let me try to go to, okay, good, the source page and show you the difference between line scan camera and the, what happened? Did I get it? No. Maybe choose some other. Yeah. Well, this one was good because it was comparing line scan and the area scan. Soda Vision, whatever it is. Okay. The satellites that orbit the Earth, the observation satellites that take the images of the Earth all the time, they are line scan cameras. So this line scan camera is moving on this image, on this target, and every time it gets a single line. When this moves from one position to another position, okay, you get another line and another line. So each line would become your columns, and if you put them together, you get two-dimensional image. Area scan camera just takes two-dimensional images all the time. Okay, so that's the difference. With the satellites, I have the same effect. Line scan satellite. They don't take two-dimensional images because the satellite is moving all the time. Okay, so instead they have a very nice one-dimensional camera like that one, and it is taking the images line by line, then you put them together. Sometimes you have an image by 20,000 by 4,000, right? It is very large. Okay, good. I couldn't find the exact image that cameras. Oh no. I wanted to show you the camera itself of the satellite. I couldn't find it, sorry. Okay, so that's it for this chapter. Do you have any questions about the camera geometry, that kind of stuff?
I have a question.
Sure.
I thought, think about a flower that we are photographing it. At the same time, we displayed it to a monitor. Before this day, I thought in the light of power of light, which came to sensor, is formed to a matrix, a Histogram maybe, and then we manipulate it to enhance it or something else. But I think now we are not talking about a matrix point. We are talking about a matrix, but we have lines, vectors.
Yeah.
Is it right? We are talking about lines, not dots. Did I understand right? Because it's very hard to understand.
Well, actually, I mean, it depends on the problem at your hand. If you are going to talk about three-dimensional world, then it is much easier to express everything in homogeneous coordinates, and it is easy to talk about the vectors. But if you are going to do image processing, image in and image out, then you don't have to deal with the homogeneous coordinate system or the three-dimensional world or the vector representations. All you care is just two-dimensional XY integer pairs, right? Second column, third row, that's it. Okay? Depends on what you are doing.
I want to know about the depth of image.
If you like to talk about the depth, then you will have to talk about the homogeneous coordinate system, okay, and inferring the depth from these two-dimensional points. Well, in that case, you are doing three-dimensional computer vision, which is the main topic of this course. This is not an image processing course. This is three-dimensional computer vision course.
It's a new point of view for me, and it's very interesting.
Sure, yeah, well, it is interesting, yes. I mean, but using a single image, it is really difficult to get the depth. You need more than one image. So that means that you need another camera, or you need to take video of the same image while the camera is in motion. So that's why we are going to look at them separately. More than one camera or camera in motion. Okay, good. Any other questions? So, unfortunately, to be able to do something about in three-dimensional world, we need to look at the images more carefully, and I need to introduce some ideas about the image processing, commonly used techniques about image processing. So let's look at some image processing background. Okay. Let me try to find my slides about image processing. Okay, here it is. Okay, we are going to make some introduction actually. So these slides, they are mostly from University of Central Florida from Dr. Shah. I think I took most of them from him, but he took most of these slides from somebody else. And I think I mixed these with some other sources. So I don't know where I got them, but these slides are not mine, sorry, okay? I don't take the credit for these. So with this topic I am going to talk about filtering, smoothing, removing noise, convolution operation, and some image derivatives and finding the corners and etc. So image types, we already see them. These are binary images. Binary images contain only ones and zeros. Okay, so it's a two-dimensional matrix again, but it is ones and zeros. Then we have grayscale images where each pixel is a single number, single integer between 0 to 255 or larger maybe. With the color images, for each pixel we have the red, green, blue components. Remember RGB? RGB comes from the human eye. Okay, in our human eyes there are three types of color sensors. The cells that are sensitive to red and blue and green. Okay, so these are the color images. And this is how you represent the binary images: columns and rows, and zero and black. Okay, and these are the gray level images, and these are the then we have the color images which have blue, red, green channels. Okay, so you may think each channel as a grayscale image. Okay, people talk about the histograms a lot. What is the meaning of histogram? The meaning of histogram is this: I take this image, okay, let's say this is 100 by 100 image, so there are total of 10,000 pixels. So I take a statistics of how many times I have seen gray level 50. Okay, so this one says that the gray level 50 I have seen it more than 1,000 times, but gray level, let's say 25, I have seen it only 500 times, etc. Okay, so this is called the image histogram. Okay, this is called the image histogram. So image histogram tells me how frequently each gray level occurs in the image. How about this part? I don't see any gray levels above 140, right? So that means that this image is darker, right? I don't see any bright parts on this image, which is a bad thing. Why? Because if I had used all the gray images, maybe I could have obtained a more contrasty image. I am using the whole light levels. Okay, so image histogram is something like that. Okay, so there is always going to be image noise on your images. What is an image noise? Image noise is this: if you are using an electronic camera sensors, they are very good at measuring the light amount, but they are not perfect. Okay, given the same light amount, sometimes my sensor is going to produce, let's say, there is light coming into my sensor. Light is coming to my sensor. This is my sensor. Okay, it is producing, let's say, 1.27 volts for this light. Okay, after a second I measured it. Now it is producing 1.28 volts. It may happen. Okay, this light did not change but my electronic device is producing a slightly different measurement. This is called noise. Okay, and this noise is going to result in slightly different pictures of the same scene from time to time. Okay, so one of the main reasons of image noise is the camera electronics, or sometimes it happens because of the light variations, surface reflectance. Sometimes lenses are not perfect. Okay, and we assume that noise is random and it occurs with some probability. Okay, and we assume that it has a distribution. Usually we use Gauss distribution to model the noise. You would say that additive noise, this is 0.0. Usually I don't have much noise, but sometimes I would get 1.0 additive or minus 1.0 subtractive. Okay, so the amount of noise that you're going to add to your image is proportional to this distribution. You take a sample from this distribution and you add it to your image. Okay, and so since Gauss distribution is very well understood and it is very convenient to use and it is realistic too, we usually use Gauss distribution to model our noise. Okay. Why modeling the noise is important? Because once we know the model of the noise, then we can do some tricks. We can develop some techniques to get rid of the noise or at least lessen the effects of it. Okay. Well, it looks like I am out of time for this week. Are there any questions? Are there any questions about this week's classes, lectures, or the one that we started right now? Next week I'm going to continue with this one, with the noise and everything, and then we will talk about this derivative stuff. Derivative is going to be important because we like to take derivative of the images, türev in Turkish, right? Derivative of the images in x and y directions. While we are taking the derivative, we are going to see how the image changes from one pixel to another pixel. That's going to give lots of ideas about what interesting stuff happens in our images, such as the edges or corners or the constant regions and etc. Okay. Good.
Hocam, I had this course on last week on Adropic.
Yes.
Will you share these slides?
I uploaded the slides in my Teams page. Also, you have the syllabus available in the Teams page in the files area, okay? They are all there. Also, the videos of the last week and the previous week is available at the Teams page, also on my YouTube channel.
Thank you.
So watch the videos of the first and second week and you will know all the details about how we are going to go with the course generally. Okay, any other questions? Good, I will see you next week then.
Thank you. See you.
Thank you. Bye.